Okay, let's unpack this. Today we are diving deep into one of humanity's biggest mysteries, consciousness. I mean, how does your experience of the world, actually arise from the wet, squishy stuff inside your skull? And and this is the wild part, what if the very fabric of that experience is shaped by the incredibly strange rules of quantum mechanics? Our mission in this deep dive is basically to explore this really mind-bending idea. We're pulling insights from some fascinating new research, highlighted by the Allen Institute, and we'll also draw from new scientists to help us sort of wrap our heads around just why the quantum world is so weird to begin with. All right, because here's the hook for you. Your brain, it's made of subatomic particles, and these particles, they just don't play by everyday rules. Not at all. They can exist in multiple states at once, or you have entangled atoms that can interact instantly across, vast distances. So the question is, how could your unique mind possibly arise from something so fundamentally bizarre? Let's start by immersing ourselves in the quantum realm itself, because as New Scientist puts it so well, it's just plain weird.
It really is.
Yeah.
That's a good word for it.
We're talking about particles that can, exist in two places at once.
Uh-huh. Or waves that don't exactly wave like you'd think.
Right. And objects whose behavior can depend on things happening, on the other side of our universe?
Exactly. It sounds completely counterintuitive.
It really does, straight out of science fiction.
Yeah.
But it's supposedly the fundamental reality of the very small.
It is. Which makes you wonder, doesn't it? Is our everyday reality just a kind of macroscopic projection of something far, far stranger underneath? And what's fascinating here, I think, is that the mathematics, the way we describe the quantum realm, it's actually surprisingly straightforward, very precise, in fact.
Okay.
But it's our human attempt, to translate these ideas into the everyday world. That's what makes it feel so strange, so counterintuitive.
It really challenges our common sense.
Completely. And this raises a really important question for our deep dive today. If these phenomena are so peculiar and they require such extreme conditions in our labs.
Right, like super cold temperatures.
Exactly. How could they possibly occur within the familiar, warm, and, let's face it, wet confines of your brain?
Yeah, and that question, that leads us right to the core puzzle, doesn't it? Some scientists are actually starting to speculate that these strange quantum happenings might hold the key to understanding consciousness itself. Which is a pretty bold leap.
It is a bold leap, and it's crucial here to bring in Christoph Koch. He's a highly respected investigator, meritorious investigator, actually, at the Allen Institute.
Okay, Koch.
I know the name. Right. And what's particularly fascinating about him is that despite, decades spent rigorously studying the link between brain matter and conscious minds, he was initially quite skeptical of this whole quantum consciousness idea. Very skeptical.
Okay.
Oh, yeah. He even famously wrote in his book, Then I Am Myself the World, something like, the brain is wet and warm, hardly conducive to subtle quantum interactions.
Wow. That's a pretty strong statement from a leading mind in the field.
It is. It sets a baseline of skepticism.
So that feels like a massive shift for someone so established. What do you think might have been the turning point for Koch? Was it one piece of evidence, or maybe just the elegance of a new idea that, changed his mind enough to collaborate?
It seems more like the latter, actually. A willingness to explore novel theoretical frameworks. Because despite that profound skepticism you mentioned, Koch is now collaborating with scientists from Google Quantum AI universities worldwide.
Google Quantum AI.
Okay, and here's where it gets really interesting. They've actually published a novel theory, published it in the journal Entropy, on these potential links between quantum mechanics and consciousness.
Wow. Okay. So how does this new theory connect with what we thought we knew, the previous ideas about quantum consciousness?
Right. Well, many existing quantum theories of consciousness, they traditionally hinge on this idea of superposition.
Superposition.
Yeah.
Where particles are in multiple states at once until you look.
Exactly. Until they're observed, basically.
Yeah.
At that point, they collapse. That's the term, into one definite state. Now, Roger Penrose, the Nobel-winning cosmologist, and the anesthesiologist Stuart Hameroff, they famously suggested something. They proposed that each time one of these quantum superpositions collapses, so when a particle picks one state out of many possibilities, it creates a tiny fundamental spark of what they called proto-consciousness.
Proto-consciousness.
Yeah.
Like a building block.
Kind of. And these sparks, they theorized, are then woven together, woven by these tiny structures in our neurons called microtubules.
Right, the microtubules.
To create our continuous conscious experience.
Okay, so Koch and his team, they knew about Penrose's work, Hameroff's work. But then they propose the opposite.
Exactly the opposite.
Their innovative twist is that conscious experience arises whenever a quantum superposition forms, not when it collapses.
Correct.
That feels like a really significant difference.
Yeah.
Why make that shift?
Well, it has a very practical benefit, actually. This approach neatly avoids the implication of faster-than-light travel, which the original collapse theories sometimes seem to suggest. The issue there was, if entangled particles instantly influence each other across vast distances when one is observed or collapses.
Yeah, that breaks physics, right? Einstein wouldn't like it.
Exactly. It seemed to challenge our understanding of cosmic speed limits, fundamental laws. Koch's theory elegantly bypasses that whole problem.
And this, it sounds like a small change on the surface from collapse to formation, but it sounds like it has some pretty profound implications.
It absolutely does. If you step back and think about the wider impact, Koch's theory suggests a kind of graded model of consciousness.
Graded, meaning like...
levels.
Yeah, levels or complexity. It's a complexity correlates directly with the number of potential states in that superposition. Now, this isn't maybe so surprising when you think about how consciousness develops, from infancy to adulthood. It gets more complex.
Sure, that makes sense. But it also implies, and this is the big leap, that at least simple forms of consciousness could be far more widespread than we conventionally assume.
Widespread where? Like in animals?
Yeah.
Or
potentially, but maybe even beyond that, in places we haven't even considered. This isn't just a theoretical curiosity, you see. It forces us to fundamentally reevaluate how we define life or awareness. Could a complex AI or maybe even certain non-biological systems possess some rudimentary form of experience? It really blurs lines we've always drawn.
And if that isn't enough to make your brain tingle a bit, Koch even contemplates what he calls a total science fiction consequence.
Yeah.
Linking your brain with a quantum computer could theoretically expand your consciousness. Though, he's quick to add, he thinks this is pretty unlikely to happen in his lifetime.
Probably wise.
But okay, beyond those really mind-bending possibilities, the burning question for any scientific theory, however bold it is, has to be, how do you actually test it? How do you put it to the test?
Right. It does sound like something out of a movie, doesn't it? But they are trying. There was a study back in 2018 from researchers in China. It involved xenon, the noble gas.
Xenon, yeah, used in anesthesia sometimes, right?
Exactly. Known for its anesthetic properties. They explored how 4 different isotopes of xenon. Now, these are chemically identical, but they differ in their spin.
Spin. What's spin in this context?
Think of it like a fundamental quantum property, sort of like a particle having an intrinsic tiny magnet or maybe an internal direction. It affects its behavior at that subatomic level.
Okay, got it. Different spins.
Right. And they looked at how these different isotopes affected consciousness in mice.
So when they introduced these different xenon isotopes, what actually happened? What specific measurable effects did they see in the mice's consciousness? And how did that, for you or for them, suggest a quantum link?
Well, intriguingly, what the researchers observed were different anesthetic effects.
Different effects from chemically identical stuff.
Precisely. Some isotopes had a stronger impact on the mice's consciousness than others. So the broader implication here, the suggestion, was a potential link between these quantum processes, the spin, and the modulation of consciousness. Koch and his collaborators, they hypothesized that the xenon form with a larger spin value might somehow create larger superpositions in the brain. And those larger superpositions could, in turn, correlate with more complex conscious states, potentially counteracting the anesthetic effects. That would explain the difference they saw.
Okay, that's a fascinating connection, even if it's, preliminary. So the Chinese study gave us a hint, a possibility.
Yeah.
What's the next step for Koch's team? How are they trying to solidify this link? What are they specifically looking for? And you mentioned flies and lab-grown cells.
Yeah, absolutely. Koch and his team are now actively trying to replicate those 2018 results. They're doing it in flies and also in lab-grown human brain cells like mini brains or organoids. And they're looking for exactly those same differential anesthetic effects based purely on the xenon isotope spin. We should see results, they think, within the next few years. And look, if they are successful, if they can replicate this, well, these findings might just shatter Koch's own initial skepticism.
Yeah.
It could open up a whole new avenue of research into consciousness. But, of course, we have to be realistic. There are still significant hurdles, big ones.
Like what?
Well, the main one is that many scientists, probably most, strongly believe the brain's environment Warm, wet, messy.
Yeah.
It simply can't sustain these delicate quantum processes.
Right, that warm, wet brain problem again.
Exactly, especially when, today's quantum computers need conditions colder than the vacuum of outer space to work.
Yeah.
It's a fundamental challenge, bridging that huge gap in conditions.
That is a significant hurdle. That warm, wet brain versus the supercooled quantum computers. How do the proponents of this theory even address that fundamental thermodynamic challenge? Is there a hypothesis for how the brain might get around it? Maybe in a localized way, or just for tiny moments?
Yeah, that's precisely the million-dollar question, isn't it? And while there isn't a definitive mechanism nailed down yet, the idea isn't really that the whole brain is acting like a macroscopic quantum computer. That seems unlikely.
Okay.
Instead, the speculation centers on specific neural structures. Again, maybe those microtubules. The idea is they might act as sort of quantum cages, or isolated little environments where these delicate quantum phenomena could briefly occur, just long enough to influence brain activity, even within that generally warm, wet environment.
So localized and short-lived effects.
Potentially. It's an area of really intense theoretical development right now.
So where does all this leave us? What does it mean for the future of this research? Despite the daunting challenges and those really strongly held opinions on both sides, Koch himself, it seems, remains remarkably open to the possibilities. He stated, and I love this quote you found, "Anything that isn't ruled out by the laws of physics can be exploited by evolution."
It's a great quote.
And as he points out, evolution's had, 4.5 billion years to play with the entire planet?
Yeah.
That's an incredible amount of time for nature to stumble upon some pretty clever solutions.
And that really speaks to Koch's powerful philosophy, I think. He also said what makes science uniquely powerful is that you can have strongly held opinions, but you can test things by asking nature a question.
Mm-hmm. Ask nature.
Exactly. It's all about letting the evidence guide the understanding, ultimately, no matter how strange or, counterintuitive the implications might seem at first.
Well, it's been a truly fascinating journey, this dive into the potential quantum underpinnings of consciousness, from just the basic weirdness of the quantum realm itself to these groundbreaking, yet still highly speculative theories and experiments. It really feels like a field where the biggest breakthroughs might still be just around the corner. Or maybe they're impossible. We'll see.
We will see. And maybe here's a final provocative thought for you, for everyone listening, to consider. If Koch's theory is correct, or even partly correct, and if the formation of quantum superpositions really does imply that simple forms of consciousness are far more widespread than we currently understand.
Yeah.
What implications does that have for how we define consciousness, how we perceive it in the universe around us, beyond just human or even animal brains?
Mm-hmm.
Could consciousness be, in some way, a fundamental property of the universe itself, rather than something that only emerges in complex biological systems like ours?
Wow. Okay, that's definitely something to chew on. A universe potentially shimmering with simple consciousness.
It's something to think about.